let me start by giving you already the main result of the paper. So the main result is that we have a nice algorithm for building all defect networks in two-dimensional Yang-Mills theory. And in this project, we consider in particular compact, connected, simple gauge group, and orientable surface. That's the main result. And let me tell you a little bit of motivation of why do we care about defects. So defects are order parameters for the phases of the theory. So for instance, in 4 dimensions, if you want to prove confinement, you have to compute the expectation value of Wilson lines. But actually in this paper, they showed that this is not enough. The information contained in line defects is not always enough. Sometimes to fully specify the phase of your theory, you have also to look at surface operators, for instance. So this is to motivate the fact that somehow this information is spread among all the defects of your theory. Then we all know that defects are related, topological defects generate higher form symmetries. So somehow the defects also encode the symmetries, the generalized symmetries of your theory. And for this last point here, this was maybe the main source of inspiration for us. We borrowed this from the study of topological quantum field theories. Mathematicians have carefully defined and classified topological quantum field theories, and it turns out that the definition, and hence the classification, heavily relies on defects, and in particular on defect networks. So this is just to say that defects in their most general form, which is defect networks, seem to carry some profound and defining information about your theory, some very core important information. So given all of this, do we have an algorithm for constructing all defects? Well, in conformal field theories, there is something like this. There's a state operator correspondence. But when it comes to extended operators, things get more difficult. And in topological quantum field theories, there is some sort of algorithm which links again to this definition. I won't have time to talk too much about this, but these are all very nice references. And I should mention that recently there have been attempts to extend this framework also to non-topological quantum field theories. But as for today, there's still no general algorithm in quantum field theories. And this is the issue that we wanted to tackle with this project. So we want to explicitly build defect networks, hopefully also have an algorithm, for a non-topological quantum field theory for the first time. And the chosen setting for this is two-dimensional Yang-Mills theory. Two-dimensional Yang-Mills theory is a very special theory. It's almost a topological quantum field theory in the sense that it's invariant under area-preserving diffeomorphisms. And actually, the weak coupling limit, it really becomes a topological quantum field theory. But most importantly, it's exactly solvable. And it has been solved in many, many different ways. I will be talking about this, but in this talk, I will never use any of these particular properties of 2D Yang-Mills. Rather, I will use them as checks. So this will not rely on any of these particular properties of 2D Yang-Mills. We just care about exact solvability because this makes the theory simple enough so that we can explicitly compute everything. And I will be working on 2D Yang-Mills on the lattice. This is a very schematic, brief review of how to put 2D Yang-Mills on the lattice. So first of all, you have to triangulate your manifold. And once you have triangulated your manifold, the basic building block of your triangulation looks a bit like this. It's just a triangle, and we call this a plaquette. Then you assign degrees of freedom to your edges. These are the U's. These are just holonomies. And you also have gauge transformations at the corners. To which plaquette you then have to assign an action, a function of your degrees of freedom. And this is not unique on the lattice. But there's a canonical choice given by Migdalt. And we will be using this particular action that I denoted gamma because it makes the theory explicitly refinement invariance, refinement invariant. And this is the crucial property of 2D Yang-Mills. This is the reason why it's exactly solvable. So refinement invariance is this statement here. So if I start from a triangle to which I assign an action gamma prime, and then I consider another triangle to which I assign the action gamma double prime, and then I glue these triangles together, a upon integrating the internal degree of freedom u in the absence of defects, I get precisely the action associated to the bigger square. And this is highly non-trivial. In 3 and 4 dimension, this is not true, right? Because you would get some terms coming from the renormalization of your theory. So this is very, very non-trivial. And this is the reason why 2D means is exactly solvable. This is equivalent to taking the continuum limit of your lattice theory. To take the continuum limit, you have to take the lattice spacing to 0, and at the same time the number of plaquettes to infinity. So this is, but doing this is not changing your theory, right? So this is telling you that 2D and Nielsen, the lattice is already the continuum theory. And let me also flash how the partition function looks like. The only important thing to notice is that it's very simple, and it's organized as a sum over irreducible representations. Okay. And this was the state of the art as for defects in 2D and Mills when we started our project. In 2D and Mills, we can have Wilson lines, and they are described on the lattice as characters in a representation alpha of the polynomial. So they are described as functional of the classical degree of freedom. We also have Wilson points. Wilson points are described as disorder operators. So basically you have to poke out a point of your manifold and then prescribe some boundary condition along the missing point. And then we have discrete theta angles. We would like to think about this as space-filling defects. And the important thing here, the only thing that I want to tell you is that they are realized on the lattice as restrictions on the allowed representations that we are summing. So remember that here we have sum over irreducible representations. If I somehow restrict this sum, this is equivalent to adding a theta term to the theory. This was the state of the art. As you can tell, all the defects are described in a different way. They're not in the same footing. So if we want to build defect networks out of these, it's not easy. It's not an easy task. So the first thing we wanted to do is to put all the defects on the same footing to have a sort of a unified description. And the proposal that we have is as follows. Our proposal is to enrich the lattice description by adding enough degrees of freedom to be able to accommodate all defects as functionals of classical degrees of freedom. So this is what the new plaquette looks like, our enriched plaquette. We still have mononomies associated to the edges of the plaquette. Now I have to assign degrees of freedom also to the corners. And we pictorially describe this as having these bites taking out of the plaquette. And we assign V degrees of freedom to the corners. Both U and V degrees of freedom live in the group, are group values. And we also assign degrees of freedom to the interior of the plaquette. These are discrete degrees of freedom that live in the center of the group. As you can imagine, with this prescription, we expect to be able to realize Wilson lines as functionals of these U degrees of freedom, Wilson points as functional of these V degrees of freedom, and theta angles as functionals of this B degree of freedom. So we have made this proposal. We should make a few checks to see if it's reasonable. As I told you before, we never appeal to the special properties of 2D units, but we do have to check that along the way they are not spoiled. In particular, we have to check that refinement invariance still holds. I will not show you the detail of the equations. All the careful proofs are in the paper, but this is what it looks like in pictures. So refinement invariance still holds. We also checked that, of course, we added new degrees of freedom. If we integrate out all of these degrees of freedom, we should be able to recover the original partition function, the one that I showed you with the sum over irreducible representations. And we indeed recover the partition function. And the last check is that if we integrate out the B degrees of freedom with this particular choice of weight, this is not very important, we recover the partition function with a discrete theta. And this is what the partition function looks like. So as you can tell, there's a restriction on the allowed, on the representations we're summing up. So this was very schematic. If you want choose a consistent orientation for all of these lines and assign representations. Once we do this, we will get terms like this. So this is just the matrix, represent the matrix element ij of the group element u in the representation alpha. So these are just matrices. And if we zoom into each triple intersection, once we have assigned representations and chosen orientations, we recognize something very familiar. This is just the tensor product of the representation alpha 1 and beta 2 going into the representation beta 1. So we know a very beloved invariant tensor living in this vector space, which are Clebsch-Gordon coefficients. So what we have is that we have a bunch of matrices associated to each segment, and then we can contract the indices of these matrices with Clebsch-Gordon coefficients. And an example will make this clearer. This is what it looks like. These are our building blocks. So you should really think of these as living at a point. So this guy is inserted at a point in the lattice. So you would have some plaquette here, some other plaquette here, and some other plaquette here. And it really acts as an operator on the U and V degrees of freedom. This is a three-line junction, but these n-line junctions depend on some data that we need to choose, and the data are precisely the representations that we dress them with. And last thing, notice that this is not gauge invariant yet, because we have uncontracted indices at the ends of the external lines. So now that we have our building blocks, we define a set of operations on these building blocks. We can consider composition. So this is a composition between two three-line junctions. You just have to choose a consistent orientation on this line and identify the representation. Then we can consider fusion. Fusion is just composition followed by squeezing the internal line to 1 until the two junctions kiss. And the last operation is called degeneration. We can also erase lines, and given that the data associated to the lines are representations, it makes sense that the way to erase lines is taking the representation to be the trivial one. And we can erase both external or internal lines, but these operations are just on internal lines, external lines only. Okay, so this is our set of operations. With this set of operations, we can finally build the basic gauge invariant object just by composing enough n-line junctions until there are no external legs. And then a generic defect will be a weighted linear combination of these gauge invariant defects. So now I can give you a very simple prescription, a very local prescription for building a defect network. You just have to insert your preferred n-line junction in between plaquettes, and then you have to integrate out all the degrees of freedom with the appropriate weights so that you can recover the partition function with the defect inserted. Okay, this is very nice. I've shown you that this is a huge set of defects, right? I should show you that at least we can recover all the known ones. So here I'm showing you that the Wilson lines are in our set of defects. So of course there are, here I'm going to show you the pictures because it's very intuitive and it's very easy to see. Everything is backed up by equations. So if we start, for example, from a two-line junction, we can recover the Wilson line just by erasing one of the internal lines. We can also recover the Wilson point in the obtuse way if, again, we start from a two-line junction and this time we erase the external lines, we end up just with a point operator. And notice that, as I promised you, the point operator is precisely a function of the degrees of freedom. It's not described as a disorder operator. And there are more less trivial checks that we can do. There was a known defect that was discussed in one of the papers that I referenced earlier. These are just two intersecting Wilson lines. This is known as IRF crossing. And we can recover this by choosing a four-line junction, erasing a line, and then you have to integrate over all the degrees of freedom with this awful way. But the most important thing that I would like to show you is closure under fusion. So you might argue that with the operation that I gave you, if I fuse a three-line junction, I might worry that I get a new four-line junction that is not in our set. In the paper, we checked that if we fuse two three-line junctions, and this is the particular way that does the job. See here, there's a U5 sent to 1. We get a linear combination of the four-line junctions that are already in our set. So our set is closed under fusion. And this is showing you also something very nice. You can argue from this that there's only really one fundamental building block in our set, right? It's just a three-line junction, because we can get 2 and 1 or 0-line junctions by erasing external lines, and then we can get higher line junctions by fusing enough n-line junctions. So this is very nice. This algorithm is looking clear and neat and simple enough. So let me give you a brief summary of what we've done. So we have an algorithm for building defect networks into the unions, and this algorithm really relies on just one building block. And this algorithm is complete in the sense that I was able to recover all the known defects, and it's closed under fusion. And we obtained this by adding enough degrees of freedom so that we could realize all defects as functionals of classical degrees of freedom. And I hope that I convinced you that this is a very easy way to describe defects, a very functional way. And everything is manifestly local and is compatible with all the nice properties of 2D elements. The last remarks I wanted to use, I wanted to say, is that, again, we never appeal to any of the special properties of 2D elements. We just use them as checks. Moreover, we were in a lattice framework, but the lattice approach is believed to be applicable to any dimensions. And this way of describing defects as functionals of classical degrees of freedom simplifies things a lot, and it's intuitive, right? At least in Lagrangian field theory, it's reasonable that defects could be thought of as something of this kind. So this is just to motivate that there is no obvious obstruction to using this strategy to other theories or even higher dimensions. It might be very hard, probably it is very hard, but there's no obstruction. And this gives me the chance to talk about the future directions. In the future, we would like to try and see if we can apply this to higher dimensions. For example, in 3 dimensions, new defects appear. It would be easy to see if we can recover them as well in this language. And there are also, we can relax some of the assumptions on the connectiveness of the gauge group or the orientability of the surfaces to be able to recover, to get new defects. And finally, maybe a long-term goal would be to finally be able to connect to the categorical language to really make progress in this task of finally making contact between quantum field theory and topological field theory. Yeah, that's all I have for today. Thank you very much.
Thank you for a very nice talk. Are there any questions?
Were you able to compute the F symbols for these defect methods?
That's okay. Yeah, that's a good question. We didn't do that. So in this computation, something reminiscent of F. So let me give you we think that the category underlying this framework is the Raka-Wigner category, for which the F symbols are the 6J symbols. And indeed, we had to use to recover this defect network. We had to use precisely the Bird-Null-Fritz identity, which is the pentagon identity, basically the we are secretly using category theory here, and the F symbol should be the 6G symbol.
So just related to that, can you tell how anomalies of these defect networks might be related to the choice of G that they engage with?
That's an interesting thing to explore. We haven't addressed this yet, but yeah, we're trying to really settle down carefully what the category should be, and once we do that, we believe that we should be able to say something about the anomalies. Thank you very much.
Can I ask a question? Could you go to the slides where you gave graphical sets of the operations? Yeah, this one.
This one.
Yeah. So if I take the structure, which describes purely, and if I RG flow down to a 2D defect, which are given by Frobenius algebras. Frobenius algebra has multiplication, co-multiplication, and limits. Can I make contact with the structure of Frobenius algebra?
I'm not sure. I'm not really familiar with Frobenius algebras. I guess you could, but I don't really know how to answer it. So I'm sorry.
If I can ask a second question. You did this in the lattice and you recovered a fusion structure for the Wilson lines. And if I go back to the continuum, since the Wilson lines may not be topological, and if I fuse them, I would expect to pick up some sort of a position independence, some sort of a parallel shift between these lines. How would that go from the lattice description to the continuum? Where would I see the position difference properly?
Yeah. So here I'm doing the computations on the lattice, but this is really the continuum already because of the property of refinement invariance. So we can fully trust these computations as if they were done in the continuum. We haven't really fused Wilson lines themselves, we just have fused these junctions. So maybe that's why we don't see the position dependence that you were looking for. Does that make sense?
It does, but can I imagine two of the lines to be vacuum? Just have one line which should recover fusion to the continuum. But it's okay. Question on that, please. Thanks.
Does the topology of the space-time play any role in this? I guess you're Euclidean theory.
Yeah, I'm Euclidean.
But how do you see, like, if I've got a generic Riemann surface, and do you have some analog of homogeneous variance?
Okay, so we did this in Euclidean for orientable surfaces. I guess you could analytically continue to Lorentzian.
Well, I'm happy to stick in Euclidean, but how do I see, like, how do I know, how does it change if I have a different genus surface?
Oh, the genus, right. The genus dependence is encoded in the partition function.
Just by that power.
Yeah, this is the G is the genus, this is the Euler character, and everything works for any genus surface. But this is completely general. All the computations we did them very locally, so we didn't commit to a particular topology for the closed surface.
But I guess, I mean, sort of different surfaces I expect different Wilson line operators. Right?
Oh, right. Yeah, of course. That is true. So I've showed you a very huge set of defects. That doesn't mean that all those defects will be non-trivial. Actually, many of them will be trivial. And we do address this in the paper. We also show that we can see selection rules arising from the underlying symmetry structure. So yeah, this is a very big set of defects. Many of them will just be trivial.
So you have not included boundaries, right? Here, or if there are any, then I guess the 2G minus 2 will change, right? You also include the number of boundaries.
Yeah. With boundaries, you would have something like a character.
Mm-hmm. Okay.
That's how Wilson points are usually described, as boundaries.
I see. As pouches, you mean?
Yeah.
Okay.
simple to make sure I understand what you did. So like, you drew these diagrams. I mean, you had these different setups, and then you had these rules for kind of excusing things or something like that. So the defect is the end point of that process. Is that the way I should think about this? And there are different ways. So there's different ways I could get to the same defect. I can raise different lines, but you show that they're all consistently will lead to the same object, right?
Yeah.
And I guess with the question over here, if I have some other physical process like two defects coming together or interacting in some way, that's a different problem from the one that you talked about.
That's
Okay.
different. I only consider fusion of these building blocks.
Okay.
Once you build your defects, then you can consider fusing them, but we didn't
That's
do
a
that.
separate. Okay.
Yeah.